Loud. Yes. Everyone, welcome to the joint seminar between civil architecture engineering and chemical environmental material engineering. We are very happy to have Dr. Brian Haus as our speaker, and Dr. David Ching is going to introduce our speaker.
Thanks, CY. So it's my honor to introduce Dr. Brian Haus, a professor in the Ocean Sciences Department. Brian's fields include coastal hydrodynamics and ocean wave dynamics. And he's interested in structures for improving coastal resilience, which is sort of the topic today. And he's also the director of the Wind Wave facility at Erasmus. And he has multiple collaborators in the College of Engineering, several of whom are here today. So with that, Brian, please go ahead.
Thanks, David, and thank you for the opportunity to present here today. I'm going to be talking about a range of work that involves a whole bunch of different colleagues, both at Rosenstiel School and engineering and biology, marine biology. And I apologize if I don't, appropriately credit everybody along the way, but certainly this is not all the work I'll be talking about is the effort. Team effort requires a lot of folks from both staff and our faculty, and we have Landolph and Prenoy on here in particular are doing a lot of work with me in the lab now on the stuff that I'll show at the end, the coastal dynamic, the kind of coastal processes, wave dissipation of different structures. So, but start out more broadly, since it's a broad audience, discussing the SUSTAIN laboratory and what we've done and what some of its capabilities are. I'm a professor in the Ocean Sciences Department. I have a background in coastal engineering. That's what my degree is in, and have been here at the University of Miami for quite a few years. And I won't actually say how many, but it's 30 years. We'll say it. So I've been here quite a while, and I've been working on these types of problems most of the time. I've been there with different laboratories. Really, the last 25 years of that have been involved in laboratory studies. Okay, moving on. So in the SUSTAIN laboratory, I'm going to be talking today about what we can observe, like what kind of processes we're doing, what the facility is, and we'll mention, since this is primarily an engineering crowd, sure, a lot of interest in just how you can apply what we can do here to real physical problems, how we scale those to make them, valid for engineering analysis, and talk about a few specific examples, which include air-sea interaction for hurricane forecasting, basically the fluxes of heat and momentum across the air-water interface, and then look at coastal structure impacts and hybrid gray-green infrastructure for, oops, I got my thing mixed up. But there, anyway, hybrid gray-green infrastructure for coastal resilience dissipation, wave dissipation to protect coastlines. And is everybody hearing me good? All good? Yeah. See the slides? Okay. So the SUSTAIN is a wind wave facility. It's the largest of this type of facility where we have air over controlled airflow over a wave basin in the world. It's got 23-meter long. That's just the test That's just the test section part is 23 meters long. The red here you see in the upper right, that is where it's made out of acrylic. The rest of the purple and blues, the purple is the ductwork that goes into this, and the blue is where the fan is. We have a 1,400 horsepower fan, can drive winds up to 62 meters per second, which is equivalent of over 100 meters per second when you talk about what that would be in a real storm. So that's a very intense Category 5 storm. That would be we'd still be pretty limited in the kind of conditions we could look at, except that we have a 12-element directional wave generator that sits underneath the inlet of the airflow. And that allows us to scale the waves to open ocean conditions. For the design work, the CFD that you done here was done by Gacheng Zha's group in aerospace engineering, mechanical and aerospace, so this was CFD done by them in the design process to identify, what we needed to do to achieve with the particular fan size, the kind of wind flows that we wanted to get. So, we make sure that we could get reduced flow separation and get up to those kinds of wind speeds. So this was definitely a close collaboration with the engineering school, working on doing the modeling that led to the development that we did. So if you look at the bottom, the CFD, in order to prevent flow separations, you can't really see it that well, but there's 3 channels in these big elbow returns where the flow is going slower. And we do that to keep it from separating there. And again, it'd be able to achieve that wind speed. So all the design elements of bringing the flow in at the top in a big volume, going around this curve, squeezing it down into the tank here at a 10-to-1 ratio, or almost 10-to-1, and then bringing it over the water was all, achieved and with work done through this CFD analysis. And in this tech session, we have acrylic, so we can see it, so we can do like modern laser type techniques, optical techniques. We can see through the top, bottom, and sides of the tank everywhere. I was previously involved in working with a much smaller tank that was very close to the floor and the ceiling, and was very difficult to get in. So we have it elevated and away from all as much as it can, it stands alone, so that we can get different equipment around it and it can use different optical techniques to analyze it. We can use natural seawater, freshwater, and that's important for spray generation problems primarily. And here you can see the movie of what that looks like, what the tank looks like under a light wind condition. And this is the wind coming from left to right in the picture, just maybe a 10-15 mile an hour wind. And it's just, looks like a small piece of the water surface. And then this is a much more energetic condition when we're producing large paddle waves and driving along 50 meters per second, a large wind through that. And you see that there's tremendous amounts of spray being generated off the crests of these waves. And this is fresh water here. If this was salt water, it'd be even more spray. That's why we need to look at, it'd be probably twice as much spray in the water. Very different characteristics. That's why we care about the spray in the tank, whether it's salt or fresh in the tank, is because of the effect on the spray that's generated. So what can we observe in the tank? Oh, by the way, I mean, I will try to leave some time for questions, but if something that somebody really, needs to grab me at as I'm going, I'm perfectly okay with that. So vortices, we can look at turbulent processes, fluid turbulence. I see if I can show this video here, or if that's, I don't know if that's good. Is it still sharing the right screen? You guys see a video playing now?
No, just your slide.
Okay. I'll just okay, so
Yes, YouTube now.
so this is just an example of some just nice little shot of doing some vortices in the tank where we have a connection. You can see the turbulent vortex being generated of a ring vortex that's broken at the top. We can, because of the acrylic, the good view angles, we can see from all sorts of different angles. And I think we can make cool things like red and green hues. Okay, I'll switch back. to my show here. Okay. I won't do that too much. I think I waste too much time with that. Okay, I'm sorry. Let me, yes, let me close that.
Try to stay out. Try to stay up.
All right. Go back to my screen here and just continue without showing the videos, I think. So we can look at a lot of turbulent processes and like this would be LAF image of a jet. So we can look at these. A lot of what we're interested in for transport and fluid dynamics is, what happens with when it breaks down into turbulent flows, which are of course not easily described in any other way, or not describable analytically, or they're easy to model without making assumptions about the scales of the turbulence and things. And we can get some pretty good visualizations that apply over multiple scales, something like the Gulf Stream, but squeezed right down. And we can look at scale model studies. I put this in the talk when I had somebody ask me if they could put a full-size F-150 in my tank to look for doing studies of the airflow around. I said, well, sorry, no, we can't do that. But we do have a number of different, we can look at everything has to be scaled from the physical dimensions down to fit into the tank. We have to consider all these different processes when we are looking at studies. Here's an example of a scaled modeled study that involved some moored boats in a harbor in St. Croix, and how they were dealing with the mooring lines. And that was a pretty complicated sort of scaling of there, because we had to worry about both, not just the length scales and the turbulence scales, but all the weighting of those things and the tensions and the lines and all that. So it's difficult to really do everything in a case like that, but I think we came about as close as we possibly could with studying the motion of those vessels to determine about how they might have caused damage on the dock structure. So some of the key scaling parameters that we are concerned about include, for the winds, and I referred to this already. That's always the question: what wind speed can you develop, right? So in the center line of the wind, that's where I say the actual right at the middle point of the measurement between the air and the water, we can generate a wind depending on the water level. If the water's lower, we have to push more air through there are a bigger volume of air, so we have a lower wind speed. If the water's higher, we can get a higher wind speed, but our kind of typical maximum operational level, we can still create waves and get a centerline wind up to 62 meters per second. But then we have to think, okay, that's great, but what does that mean for over the ocean or out in the natural world? Some different ways we can scale this is like by looking at, say, the wind speed at half of the wave speed the wind speed at a height of 1/2 wavelength. That can be scalable whether you're in the lab or in the field. Or another one that we use that in right here was the relative velocity of the wind to the wave speed. Again, your scale ratio of speeds. So you can get that as a non-dimensional ratio for what we call the wave age, which can apply in the field and in the tank. But one of the things that we have to do is, I mentioned, I could say, well, how do we compare that to the real world? We use a log profile, as most of you that have had fluids heard about, I've heard that. And then we look at with a variety of assumptions. You can look at what the wind speed would be up at 10 meters if these assumptions held. So it's a very approximate way of doing it, but it's a way that we can relate in general what our wind speeds are to those that are observed out in the field, which we have to do for a lot of, for when we're publishing this compared to other facilities and things, everybody does the same thing to say, okay, this is how we can convert it to something worthwhile. And then the fetch, or the distance over which the wind is blowing, is an important parameter for a lot of these things. And here we can scale our fetch by the wave conditions and wind conditions, so that that fetch we can use a non-dimensional fetch to apply that to the field. For waves, we have different things we look at. We look at wave heights, water levels, periods, wavelengths. And again, we need to look at some kind of non-dimensional parameters in the lab to make these apply to the field conditions. So we can look at the average wave steepness, HS over lambda. We can look at an instantaneous steepness, or the slope right at that value, but at an instant and position. And again, using the 10-meter wind speed, we can apply these things to the open ocean. And then other non-dimensional parameters that come into play, which I'm sure all of you are familiar with: the Reynolds number and the Froude number. Reynolds number, the ratio of inertial to viscous forces, and the Froude number is the ratio involves the ratio of gravitational and inertial forces. So the key questions that we're addressing for the first of these applications. So just as a note, for Reynolds numbers, before I go on, I should have said this, Reynolds numbers, most of the length scales that we're typically observing in sustain allow us to easily achieve, or relatively easily achieve, turbulent flow conditions. Obviously, the Reynolds numbers of open ocean, things like that, are much, much higher unless you're approaching the boundary. But we can get in most conditions, we can get, it's energetic enough to get fully turbulent flow. So for air-sea interaction problems, one of the things that we're most concerned about is like the rapid intensification. So we're working a lot with trying to understand how we can get better understanding that process, and what we can contribute happens at the air-sea interface, where the energy that powers the storm, the heat and moisture coming off of the surface that provide the energy that allow the hurricane to intensify, will all have to get through the water surface. So whether it's water vapor coming off the surface that goes up high in the storm power, the latent heat that we see in these towering hurricane unstable turbulent vortices, or the direct sensible heat of the water, both of those contribute to the energy that goes into the storm. And then the frictional drag of the waves and the water surface on the wind is taking energy out of the storm. And we use bulk flux coefficients to scale those, and we can measure them, particularly for the heat and the latent heat transfer. We can measure that key part about what's happening right at the surface, how much of that water vapor is getting into the air and how much heat is getting there. We can't do anything about how it gets, say, from a few meters above the surface up to the hundreds of meters into the cloud. That gets there into the atmospheric models, but a lot of the atmospheric, but what they really lack, a lot of the models, is good information on what basically their bottom boundary condition is, what's coming up into the storm. So we're working to get the models better. And one of the things is this momentum flux is generally scaled by just U10, and you'll see me do that as well, by the wind speed. But it's clear that the waves have an important part to play in this, independent of just how they're directly related to the wind. And so that's one of the things that we're trying to understand a lot better, is what the wave contributions to the wind stress and with the vertical momentum flux, same as wind stress, is at the surface. And this picture was taken the last time NOAA allowed any kind of flights close to the surface, and then the P3s. This was Hurricane Isabel in 2003. It was quite a ways from the eye, so it was not even hurricane force wind conditions. NOAA flew to this plane at, I think, 75 meters above the water surface when for a study that was being done through University of Miami. When they lost an engine, and when they flew back, and they didn't try to climb out of this. There's 4 engines on the plane. It got so much salt water on it that the engine started. So one of the engines burned out in flight. They tried to go away. They started to go up slowly, so they didn't stress the engines. They did do that successfully, got out of the storm. When they landed again and stress tested the motors, they all failed. So they got too much salt water in the motors. And so they basically, since that time, NOAA has not allowed any boundary layer study. So obviously nowadays they're moving to things like drones and sail drones and flying drones and things that are not unmanned aircraft, but the last time that they were able to get that close to the surface was then. So which then it calls into, how to do this in the laboratory is really important. So this figure here shows sort of where our big contribution in the laboratory quite a while ago now, 20 years ago, was to show that the drag coefficient, if you look at, there was 2 papers that came out of Miami. Mark Powell was at NOAA across the street from us, and he was using dropsondes out of the airplanes that I referred to, the NOAA P3s. And in our laboratory, we were making measurements of the drag coefficient. That's what you see here. And both of us showed, if you looked here up until that time, the measurements, if you look at the right, went up to about 25 meters per second of what this drag coefficient could be in high winds. And or was that was where it was measured. And the practice then was to just extrapolate the drag coefficient to higher winds, keep going at this slope. And we showed in the laboratory, and around the same time, Mark Powell came to Mark Donnellan, who was my mentor at that time, and he said, we're starting to see these dropsondes that are showing a leveling off around 30 meters a second of the drag coefficient. What can that be true? And we said we were seeing it at the same time. We were seeing it in the laboratory. So we both published those, and has been used ever since in all the hurricane models that you will see. But as you'll see in a bit, there's still work to be done. So the question is, why does this happen? There's a couple of questions. Why does this happen? And really, what exactly, this is a lab study. Dropsondes have a measurement that has a lot of problems. So what is the real details of that too? Can we get better data to define that? And what is mechanistically what's happening? So the question of why does drag saturate in strong winds? Number of ideas. We continue to work on the sheltering and flow separation problem. I have a graduate student right now, Payson 10, who just published some work on that. And then the role of the spray and bubbles. You can imagine with all the spray, like you saw in the little movie there, is the water surface where the air and water interact can it still be represented in a simple way, or when you have this kind of mixture of air, water, and all this? And then what role does just the direct ripping apart of the top of the wave have? So flow separation, when I say that, this is what I mean. It's like the flow coming over that, and you get behind the wave, you get these separation zones. And so once that happens, then your relationship between the wind and the drag changes, can change quite a bit. And if you get enough of these flow separation and saturation events, is that what's causing the drag to saturate? So on the right hand side, you see some PIV work done in a lab. This was done at the University of Maryland, or University of Delaware, sorry. And then Mark Buckley has also done some work in our laboratory and done some recent measurements similar to this in higher winds. And then the spray and bubbles, as I mentioned, there's this question about whether it forms a multi-phase layer. And wave tearing by wind would mean basically that the surface of the waves, as they get strongly wind forced, are destabilized and are no longer represented by this kind of canonical or by the anything close to what we use in normal wave theory. That's why the drag coefficient would be so much higher. But this is some measurements, again, from the Verone lab of showing some of the spray, and then we've made very similar observations in sustained. And then this is looking at what this, some other work that looked at what happened in the high winds. This is about all that's available in the field, was these images looking at the streaking and the flow and the bubbles and foam that are present in extremely high winds. And this type of work is all leading to, okay, so we know what the drag is up to. We know it saturates at this point. Does it continue to saturate like we showed it here? And this is up to about, you can't see the thing on that's about 650 going like that, 50 meters a second, or does it fall off? Now, a lot of the measurements that are made of this fall off region up here are pretty shaky. So we're not sure that that's exactly what's going on. So that's one of the things we're trying to do more of. And the way that we do this in the lab, to make all these measurements is basically, it's so hard to measure exactly with the wind stress, say with a hot film anemometer or a laser Doppler anemometer. There's so much spray and things in the air, and it's really difficult to measure. But we can do a bulk measurement by looking at the momentum budget of wind and wind and waves coming in the slope of the surface. And from that, we can back out the wind stress part of that and the drag coefficients. So that's been done, and this is a picture from our smaller facility, and you see that type of work going on, of measurement being made. This is a view of the waves as they develop. I'm gonna move forward a little bit quicker now, so we can get to. Well, I'll just gotta show the punchline. But anyway, in the end, when we did this, we did an NSF project, and we made the mistake of a experimentalist of trying to repeat our work to show that we could do it again 10 years later with different instrumentation, but the same facility. We ended up getting different results, which was pretty distressing as the first phase of the grant. That was our calibration part of it. We're going to show we can do it. And in the end, we went back, we being my colleague Millen Kursik mostly, went back and discovered that the original analysis, there was a mistake in one of the calculations, and that we actually shifted our data, the original data, slightly higher. So you can see here the red and the black, which is pretty painful process to go back a decade. And this is widely used in a lot of modeling, and have to correct it, but we did it. And it's now, in some ways, we're much happier with the way that it matches. If you see here, some of the lower wind speed data that's available to these stars, Edson et al. We're very close to that. We still match some of the higher data better too. So it's a better match with other studies that have been done since and before. And anyway, so we've corrected that, and now that value is being used in a lot of things. And then we're also continuing to look at what the paddle waves do, what the wind waves do independently. See, all that was scaled on wind speed alone, but in like a hurricane, the winds are coming from different directions, the waves are moving from different places. And so your waves are not always directly coupled with the wind. And so we need to look independently at what the waves can do. And you can see that can have a dramatic effect on the things. If you look in this bottom plot here on the right, you see that, well, the two plots on the right, you see that there's much higher drags when you have additional paddle waves in there. So the question now is, how do we get that in a form that can be usable for the forecast modelers? Obviously, they may not have a good wave measurement, so the independent wave measurement is in many places as they have wind speed, so that may not be that useful. But if you do have the information, you can clearly should be able to get a better representation of what the actual stress is. Now, I'll just move a little bit beyond this. This is some work on how this is done how this is distributed in frequency and fetch, the wave heights that are developed. And then for the tearing, this other hypothesis, this is the slide just about that. It's where you get this direct disruption of the wave surface, and that can contribute to this stress flattening as well. You see it from the top and the bottom, you see the change in the dominant wave spectra here, the green line, when you have the wind and the paddle wave, that it's damping that as the winds get very high. And then we're interested in a lot working with Dr. Barbiegos. Landolf is on here, looking at coastal structure impacts and what the role of winds and waves are together on those. And this is tied a lot to trying to protect shorelines with reefs to help to reduce these wave impacts on structures in strong storm conditions. There's things obviously that a reef cannot do, and if we get a direct Cat 5 with a strong storm, super elevated storm surge, there's probably a reef on the bottom is not going to even be interacting that much with the waves. But anyway, so we're interested in trying to quantify all these different things about how the waves, reefs affect the flow in a way that, and structures in a way that we can demonstrate or understand what the contributions of doing things like reef restoration or different types of building strategies to build better, protect the coastal communities. So coral reefs provide a natural protection because of their ability to reduce wave heights, which contribute to coastal erosion and cause additional flooding due to transport of water due to breaking waves inshore, close to shore. If we can break them farther offshore, if we can dissipate their energy, they won't bring as much of that wave setup into the shoreline, and will cause, it has been demonstrated to reduce flooding impacts for communities inshore. And we have, as we have known, that there's a lot of interest in this problem now. It's growing every week, it seems. We get new interest in how we can better protect coastal communities, and new, particularly a lot of U.S. federal money is going into these problems now, trying to protect our from the effects of increasing storms and water levels as the climate changes, of course. And let's see. So what we do in SUSTAIN is we look at direct measurements of the reduction of wave energy by the coral reefs and try to apply this to the natural world through different scaling processes. And calibrating this, we actually have an in situ program. We're putting these reefs out in the water. They have some off of Miami Beach. And we just got a bunch of data back from them for like being out in 6 months about what was happening with this reef. It's in pretty deep water, but we at least get some information from a natural reef with what's happening as the flow goes over it, with corals and other things growing on it, as well as to compare with what we're doing in the laboratory. And the idea is to quantify this dissipation, as I mentioned, this reduction of wave energy as you pass over these reef structures, and provide guidance for the field testing and permitting and things like that. So this is some pictures of some work that we did a little bit ago to understand loads on structures. We've since basically completely updated the sensing capability of SUSTAIN to do a much better job with the pressure sensors. We now have a 64-port pressure transducer that can handle a lot more pressure points on structure than what you'll see here. But as an example. And then here's a short video of these waves hitting structure, scaled structure. This was a 1 to 15 scale, I think, if I recall correctly. So 1 to 15 scale building at grade, and you can see the waves hitting the front face of that, and all kinds of things happening, shedding off the roof, and etc. And here's another example of with the same project, a different style of house at grade, getting exposed to storm conditions with waves hitting the base of that, or hitting that side of that building. And these two structures are both still both got destroyed after a while. We kept they survived the testing, but we kept using them in different purposes, and those two that are at grade no longer exist. They got beat up too bad, but we did have another one we tested that was on stilts, which did much better. So this shows, and this is work that's led into a NIST study that we're doing with Landolf, and in some ways to another NIST study that's been done with Pernod, Suriname. But the key thing, this is directly related to the NIST one with Landolf. We're looking at combined wind and wave loads on structures, because the code development is either wind or surge or waves. We can try to do all three together, have different water levels, different wind speeds, different wave conditions. And this is just the example from what we just showed, where you have the front face of the wave of the structure, which is exposed to the waves directly, and the side of the structure. And this time on the axis is also, there's the wind speed is gradually ramping up to the maximum wind speed. So you see that the wind speed, as the wind speed keeps ramping up, the waves get bigger. So you see, so the spikiness here is due to the waves hitting the structure. You see it very strongly on the front face. You also see, so as the wind goes up, at some point, it does level off here to some extent. You see these don't continue, the overall pressure loading doesn't continue to go up as the wind speed increases. However, the waves are getting bigger up to a point, up to about the same point. So those fluctuations are getting bigger, and you see that trend, that spikiness, and this is what really I would think causes a lot of the damage, is this repeated loading of the waves on the structure. It's not just it's not a steady kind of pressure applied. It's this hammering of these spikes of this, and cause a lot of obviously fatigue on those structures. And I'll just show a couple of the wave tests here. I think I've talked about it enough, showing some of the, this is a flat structure. What we're trying to do here is look at the waves over a reef, over the corals, and did the same measurement without anything, trying to understand what the frictional contribution of the corals is, as opposed to just the structural. Okay, so that's what I showed there. Okay, so then, and so because that's a question that okay, so you have put a structure out. What do the corals actually do on top of that? And so we're trying to understand that. Well, this is some work that was done by Mohammed Ghassan a few years back, working with Landolf, and this is like before and after pictures with these corals on the bottom. So you see that there is a noted effect even on the flat bottom with adding the corals in terms of taking away the wave energy. So they're increasing the roughness, but then you have this question of how much. It's a fairly short piece, so there's not a lot of distance over which they're traveling. So they're all so it's highly wavelength dependent. because that's controls how much of the time that that wave is actually interacting with those structures. So we can see that that's but there can be some fairly significant effects of that. And here's just some tests, did a bunch of different conditions. As you can see, they're very different sometimes in terms of how they interact with the particular waves. And here shows these on a structure doing the same type of measurements with that. Trying to understand what how much the corals contribute, what the shape of the structure could be, and et cetera. And shows how these were laid out. Don't want to take too much time here, so I'll just go. And then this is some work that we did looking at the waves breaking over a structure and how that energy would be dissipated. And see, sometimes the wave, one of the key things with this, the wave is not always the frictional dissipation. We want to encourage as much as possible, because that breaks the wave energy down into turbulence and heat. Whereas if we cause the wave to break, like it shows here, what we're interested in looking at here is that transfers energy. That does dissipate some energy directly to turbulence, but it also transfers energy to different wave components. And if you're not careful about it, you can actually transfer energy to longer wave components that propagate further up the beach. And so that break off, if the break's at the wrong point or too energetic, you can cause that to penetrate further in the water. That can actually increase the wave setup at the coastline and increase coastal flooding. So that's something we have to be considering. We're looking at the details of these things. And that's okay. That's why we've moved on to the SEAHIVE type project, where we use designed elements to try to enhance the dissipation, as opposed to having them be purely inducing a wave break or purely reflective. That is a good point to stop, I guess. If there's any questions based on this, it'll be, or what I've shown, and leave enough time to have a few minutes for that. David?
I'll ask a question,
Yeah.
Brian. You know, the wave in the wave tank, the waves are propagating normal to the structure. Is that a worst case scenario, say, compared to the waves propagating at an angle to the structure?
I think it depends on the structure and things. When we can, I mean, obviously, if we were, that's another parameter we can test if we're looking at a specific design, is you can rotate the structure, or we can generate waves at an angle in the facility as well with the wave paddles. So that is another area of interest. I wouldn't say that the straight on. I mean, obviously, if the wave is directly impacting a flat surface like was in the case of the house, that is clearly would be the worst case right then for that particular configuration. But of course, every other structure and shoreline would be different, and natural waves are going to come from all sorts of directions. So yeah, that's something that when we're doing an engineering design, that's definitely something you want to consider, is what the loads at different angles would be. And that's something with the width of the facility, we have pretty good capability to do that, more so than other wind wave facilities. There's very large wave basins that can accommodate some directional studies, but they don't have the wind as well.
Thanks.
Jane?
Yeah, so thanks, Brian. So I have a question about this drag coefficient, because I work on aerosols. So when I think about drag coefficient, I remember there's a curve plotting the drag coefficient as a function of Reynolds number. And there are some funny things happening at the tail when it goes to the turbulent region. So I'm just wondering, is that the same drag coefficient in your experiments?
Well, it's the bulk drag coefficient that relates the wind speed to the stress. So tau equals rho CD U squared, basically. U 10.
Uh-huh.
So it depends. I mean, the one that you're talking about might be more. So yes, if you're talking about the atmosphere ocean boundary layer, then that is what we're talking about, that drag coefficient.
Okay. So
So when you get to really in large winds, we show that it flattens out and some field studies have suggested it may start to decrease again and really even higher winds.
mhm, mhm.
We're
And
trying
then
to validate that now.
yeah, and will this drag coefficient affect how much sea spray aerosols coming out from the wave?
Yes, yes, it's all involved in that, the stress at the surface. Sea spray, I talked about sea spray, but I didn't show what we've shown in the measurements, in the large particles. There's definitely obviously a wind speed dependence on the aerosol production and the spray production. Question is, does it saturate as well? There's the pretty complex. I mean, I'm mostly looking myself at the larger spoon, stuff above like 50 microns. But and that the question of whether that saturates as well as the drag is still unresolved. We haven't made good enough measurements in strong winds of spray to answer that question.
I see. Thank you.
Any other questions?
I have a general question. In order to do such a research, what will be the necessary training or background? Is it going to be in coastal engineering, or is it going to be physics, or what?
The key thing is having good math and physics skills. Yeah, math, physics. I mean, engineering graduates are definitely our target for trying to bring graduate students in at the graduate level. Because you have all the required math and physics and statics and dynamics and all that, and fluid dynamics. So that's what we look for. I mean, we're getting it. We know when we're getting into some of these things now, we're mixing biology and physics. Then that's can be a little different distribution of some of the skills, but we are still really. I mean, if you don't, that's the type of students we're trying to get in. Most of our undergrads have engineering or math or physics backgrounds. Most of our graduate students.
There's one chat.
Yeah, I see.
Question.
Have you looked at the corrosion over time due to increased acidification? We are not looking at that particularly because we have our corrosion studies involve studying how much our tank is corroding when we have salt water in it and trying to mitigate that. But in terms of, because we don't run really long-term studies in the tank, there is a group right now led by Vivek Prakash and working with different concrete formulations that Prannoy Suriname has developed that are working inside in the sustained facility. We've set up some flow through tanks that they're leaving there long term to look at this question of what the effects of different formulations are for the how they decay and what they give off when they're exposed in the concrete is exposed in the seawater. So it's not really in our wheelhouse in a sense, but we can do some things towards that question.
I have another one if no one else asks. So the research conducted over here using seawater, how can we translate that to fresh water, say in large freshwater pond or lakes?
Well, we've done studies of both, because we can do both fresh and salt water. So we have the corresponding data that includes the freshwater curves. In fact, the CD that I showed, the Donnellan et al. CD, that was done in freshwater. The saltwater, is just hard. We have a relatively easy way to work with it to get it in the tank. We don't have to make it like a lot of, if somebody's that is in Illinois or something trying to study this, or Colorado, they're going to have to make their own seawater simulation. But we can just pump it out of the ocean. But it still is more difficult to deal with than freshwater. So we if we don't need to use it for a particular study, we typically use fresh.
I can just comment on that too, Brian. Your CD values that you use as a function of wind speed are the same ones that are conventionally used for lakes, except that they only typically go up to smaller wind speeds, typically 15 meters per second.
Sure.
Well, it's 12:06. If no more question, please join me in thanking Dr. Brian Haus for a wonderful seminar presentation.
Thank you.
And that concludes today's seminar. And the next week will be a town hall meeting. Thank you, everyone, for coming here today, and look forward to seeing you next time.
All right. Thank you all.
Thank you. Thank you, Brian.
Thank